Every time you shop online, check your bank account, or even just log into your email, there's this invisible shield protecting your information. Well, that shield is called TLS. And in the next few minutes, we're not just going to talk about what it is, we're going to break down exactly how it works, and most importantly, how to make it lightning fast.
So you see this little lock icon every single day, right? We're all trained to look for it, to trust it. But have you ever actually stopped and wondered what's really going on behind the scenes? How does this one tiny symbol create the secure connection that the entire internet depends on? Well, it's definitely not just a picture. It represents this incredibly sophisticated, super high-speed negotiation, a kind of digital handshake that happens in milliseconds every single time you visit a secure site. Its entire job is to build a private, encrypted tunnel just for you and the website you're visiting. And the technology that powers all of this is called Transport Layer Security, or TLS. As you can see here, it's a layer of protection that sits right between the application protocols your browser uses, like HTTP, and the transport protocols that shuttle data across the internet, like TCP. Think of it as a dedicated security guard for your data. So first, let's break down how it works, and then we'll dive into how we can make it as fast as humanly possible. Okay, to really wrap our heads around this, we need to understand the three fundamental promises TLS makes every time you connect. These are pretty much the pillars of all web security. So first up, you've got encryption. This just scrambles all the data so that even if somebody manages to intercept it, it's just a bunch of unreadable nonsense to them. Then there's authentication. This one is absolutely crucial for preventing things like phishing attacks because it proves you're actually connected to the real server, not some convincing fake. And finally, integrity. This guarantees that nobody can secretly change a message in the middle of its journey, like turning a transfer $10 request into a transfer $1,000 request. These three things working together are what create the secure foundation for the web we use today. So how does TLS actually build this secure tunnel? It all kicks off with a process called the TLS Handshake, which is this really rapid back and forth negotiation between your browser and the server. Let's walk through it. First, your browser sends out a little message called a client hello. It's basically saying, hi there, here are all the encryption methods I know how to use. The server then replies with its digital certificate. Think of it like its passport to prove its identity. It also looks at the list from the client and picks the strongest encryption method, or cipher, that they both support. Next, and this is the clever part, the client creates a brand new secret key just for this one session, encrypts it using the server's public key from that certificate, and sends it back. We'll touch on public keys in just a sec. Finally, both sides send a finished message, and boom, the secure tunnel is officially open. Now, this diagram is so important because it shows you how that handshake directly translates into time, into delay. You can see all the back and forth communication. Each of those round trips, the first one to get the server's certificate and the second one for the client to send its secret key, takes time. In this example, just between New York and London, that adds up to 112 milliseconds of latency. And get this, that's before a single byte of the actual web page you want can even be sent. This latency is by far the biggest performance killer in TLS. So, you might be asking, why this complicated dance? Well, it's because TLS very cleverly uses two different kinds of encryption. For that initial handshake, it uses the slower but very secure public key cryptography. The classic analogy here is a public mailbox. Anyone can drop a message in the slot, but only the owner with the private key can actually open it and read the mail. That's how the client safely sends the secret key. But once that key is shared, they both immediately switch to the much, much faster symmetric key cryptography for all the rest of the data, using that one shared secret. It really is the best of both worlds. You get a super secure key exchange, followed by incredibly high-speed encryption. Okay, so a common myth you still hear is that all this encryption must be a huge strain on servers. And look, for a long time, that was actually true. But as this quote from Google's Adam Langley makes really clear, that's just ancient history now. Modern CPUs are incredibly good at this stuff. So the real bottleneck today isn't the computation, it's the network latency from those handshake round trips we just saw. Right, so we mentioned authentication as a key pillar. But how does your browser actually know that it can trust a server's certificate? I mean, what's to stop anyone from just making one up? Well, this is where a beautiful concept called the chain of trust comes in. It's all based on a very simple human idea, transitive trust. Think about it this way. If you, Alice, totally trust your friend Bob, and then Bob comes to you and vouches for some new person, Charlie, you now have a pretty good reason to trust Charlie, right? You're extending your trust through a chain. The web works in the exact same way. Your browser is Alice. It comes pre-installed with a list of super trusted organizations called Root Certificate Authorities, or CAs. They're our Bob. When a website owner wants a certificate, one of these CAs verifies their identity and then digitally signs their certificate. And that creates the chain. Your browser trusts the root CA, and the CA vouches for the website.
And here's what that looks like in the real world. You can see the website's own certificate at the bottom. It was signed by an intermediate CA, which in turn was signed by a root CA that was already trusted by your browser from the very beginning. Your browser just follows this chain of signatures all the way back up to a trusted root to make sure the site is totally legit.
Okay, so we get how TLS provides security and trust. Now let's switch gears and talk about performance. For anyone running a website, this is the big question. How do we minimize the latency that all this security adds?
2. This is the number that engineers obsess over when they're trying to optimize TLS. 2, because every full, from-scratch TLS handshake requires 2 complete round trips across the internet before your page can even start to load. This is our number 1 enemy.
So, how do we fight back? The solution is a fantastic optimization called Session Resumption. The idea is simple. If you've connected to a server recently, there's no reason to go through that whole 2 round-trip negotiation all over again. Session Resumption lets the client and server just reuse the security settings they agreed on last time and jump straight into a secure connection in just 1 round trip. It literally cuts the handshake latency in half. Now, there are 2 main ways to do this. The older method is called session identifiers, and it requires the server to keep a big cache in its memory of every recent session. The newer and much better method is session tickets. With this, the server just encrypts all the session information into a little ticket and hands it to the client to hold on to. The next time the client connects, it just presents the ticket. The server doesn't have to remember a thing, which makes it stateless and way easier to manage for big distributed systems. All right, let's pull all of this together into a really practical checklist. If you manage a web server, these are the key things you need to configure to squeeze every last drop of performance out of TLS.
First, enable both session caching and tickets. This gives you the best of both worlds and ensures the fastest reconnections for all clients. Next, optimize your TLS record size so your encrypted data fits perfectly inside a single network packet. A big one, keep your certificate chain as short as possible. Enable OCSP Stapling. This lets your server prove its certificate is valid without forcing the client to go check somewhere else. And finally, implement HTTPS, which basically tells browsers to only ever talk to your site over HTTPS.
And I have to mention one more essential feature, server name indication, or SNI. Before SNI, every single HTTPS website needed its own unique IP address. It was a huge problem. SNI lets the client tell the server which website it's looking for during the handshake, which means a single server can now host thousands of secure sites on just one IP. It is absolutely fundamental to the modern web.
Here is a classic performance trap. This is a real packet capture, and it shows the server sending a certificate chain that's over 5 kilobytes. That is way too big. It's so large that it overflows the initial network window, forcing an extra network round trip right at the very beginning. The lesson here is simple. Keep your certificate chain lean. Only include the certificates you absolutely need.
And look, don't just guess about this stuff. Test it yourself. You can diagnose pretty much any server with this simple OpenSSL command right from your terminal. It'll show you the full certificate chain, the exact cipher being used, and whether session resumption is actually working. It's an absolutely indispensable tool.
So, let's say you've done it all. You've optimized your server, you've enabled session resumption, your certificate chain is tiny. But is your site fast for a user on the other side of the planet? The next performance bottleneck isn't on your server at all. It's the speed of light. It's geography. And solving that means bringing your server, or at least the TLS handshake, closer to your users. But that is a topic for another day.